Hi, everybody. I'm Andrea, and my teammate is Nicolette. And today we're going to be talking about the impact of MRI quality on automated LV segmentation, quantified through myocardial strain. So, for the background, cardiac MRIs are used to assess ventricular structure and also help diagnose cardiac diseases. Oh, sorry. Can you still see my screen? Okay. Help diagnose cardiac diseases. High image quality of these MRIs are important for cardiovascular disease diagnosis, especially for calculating myocardial strain, which is an indicator for deformation. Studies have shown that deep learning segmentations are sensitive to image quality, which can affect myocardial strain quantification due to the effect on the endo and epicardial boundary measurements. Reduced image is typically caused by motion artifacts such as cardiac motion or respiratory, and automated segmentation is typically used for faster manual since faster than manual segmentation and reduces human variability.
I do think it's only showing half the slide, but it
Oh,
still shows the important parts. Oh, there we go. So, for some background on the cardiomyopathy, we evaluated three patient groups: normal hearts, hypertrophic cardiomyopathy, and dilated cardiomyopathy. So, normal hearts demonstrate efficient and balanced contraction. Hypertrophic cardiomyopathy, or as we'll call it HCM, is characterized by abnormally thickened ventricular walls, which can lead to stiffness and impaired filling. Dilated cardiomyopathy, or DCM, is characterized by enlarged ventricular chambers and weakened contraction. And because these disease groups have different geometries, they provide a very useful framework for evaluating how image degradation impacts segmentation robustness. So our project consisted of three primary aims. First, we established baseline of myocardial wall thickness and strain for normal DCM and HCM patients. Second, we evaluated segmentation robustness under increasing levels of image degradation. And finally, we quantified how segmentation errors propagate into derived measurements such as wall thickness and strain.
so for our first AIMS method, we used the Automated Cardiac Diagnosis Challenge Dataset, or ACDC, for 15 patients in each disease group that we talked about. The ED frame was selected at largest LV cavity, and end systole frame was selected at the smallest LV cavity. We used a pre-trained segmentation model that takes the MRI image input, pre-processes it where it takes the segments or it segments it and predicts the regions by extracting the myocardial mask label. Then it identifies the endocardial and epicardial boundaries through contour extraction and takes the wall thickness measurements. Then it calculates strain using equation one below. And figure one is just an example of the GT mask overlay on a normal patient. So table one summarizes these baseline results. We measured ED and ES thickness, radial strain, and percent thickening. Here we see that DCM showed much lower strain values compared to other groups. This may be due to the physiological differences where DCM hearts contract less dramatically, so it produces smaller wall thickness changes. However, multiple of the DCM cases, about 6 out of 15, also produced ED equal to ES measurements, which can also lower our strain mean. So these baseline measurements were used as a reference for all of our degradation comparisons. And figure one is just an example of all the baseline myocardial wall thickness measurements that we took. So as expected from ED to ES, it increases due to contraction. HCM shows much thicker myocardium than other groups, and DCM shows the relatively small ED to ES changes that we just talked about. Normal hearts contract more strongly, so they can create larger boundary movements between frames, so this can increase sensitivity later on. So these results just showcase that the baseline segmentation was relatively robust to move forward with the rest of the aims.
To evaluate segmentation robustness, we simulated two common forms of MRI degradation. First, Gaussian noise introduces random intensity fluctuations and mimics scanner noise, which reduces image contrast. Gaussian blur smooths neighboring pixels and simulates reduced spatial resolution or motion-related image degradation. And for both degradation types, we applied low, medium, and high levels and compared the results to the clean image. For GT labels, okay, sorry, excuse me. The image on the left, you'll see predicted labels and GT labels. And for the GT labels, they represent true myocardial boundaries, while the predicted labels show the model segmentation output, allowing us to evaluate segmentation accuracy through their agreement. So a close overlap between the predicted and GT labels indicates strong segmentation performance. This slide shows representative examples of increasing blur and noise levels for a normal, healthy patient. And as degradation increases, anatomical boundaries become progressively harder to identify. And since segmentation algorithms rely heavily on boundary information, we expect segmentation performance to decrease as the image quality worsens.
So to evaluate that, we calculated the dice score, and this measures the overlap between the predicted segmentation and the mask. So here we're showing the blur for ED and ES across all disease groups. Increasing the blur generally reduced the dice scores. The largest decrease occurred at high blur levels specifically, particularly in the normal and DCM groups. HCM maintained relatively higher, suggesting maybe that thicker myocardial walls may be more robust blur degradation for segmentation. And overall segmentation performance slowly decreased over degradation of increased blur. And then we also did the same thing for noise, and it showed us somewhat of a similar trend. However, once it hit the high noise, it degraded completely for the dice score. Um, Here, the ES measurements appeared slightly more sensitive than ED, and this may suggest that the image noise artifact or affects boundary detection more severely during contraction. So segmentation stayed strong, but until high noise was introduced, then it exponentially dropped off.
So, unlike dice score, Hausdorff distance measures boundary disagreement between segmentations. So, lower values essentially indicate better boundary accuracy. As blur increases, Hausdorff distance rises slightly across groups in ED, showing that boundary localization becomes less accurate. However, the Hausdorff distance stays relatively constant or consistent in ES segmentation. This indicates that even when overall overlap remains relatively high, boundary errors begin to accumulate. Similar trends are observed with Gaussian noise. So increasing noise levels produce larger Hausdorff distances, indicating worsening boundary precision. Together with the DICE results, these findings show that image degradation consistently reduces segmentation performance. And for AIM-3, we investigated how segmentation errors clinically affect clinically relevant measurements. Wall thickness was extracted from degraded segmentation masks, and we then calculated radial strain and percent thickening and compared those values to baseline measurements. And finally, measurement error was quantified using thickness error, strain error, percent thickening error, and thickness RMSE. And you can see the equations that we have used in this table in the bottom right in table 2.
So here we're just examining the strain error versus the degradation level for both noise and blur. As you can see, the strain error generally increased as degradation increased specifically for normal and HCM patients, but that showed a much lower error compared to DCM patients. So even though we just said that ECM had a slightly higher dice score previously, it could show that derived measurements could still deteriorate even if the overlap is good. So small segmentation boundary changes could cause a larger strain error.
This table essentially summarizes average measurement errors across all groups. So although segmentation performance decreases with degradation, the resulting measurement errors remain relatively modest. HCM and normal patients generally exhibit larger errors, while DCM patients appear less sensitive to degradation, as you can see in this table. And these findings suggest that segmentation errors do not always translate directly into large measurement errors.
So for our discussion conclusion, we want to talk about the future work and limitations. So some limitations of our current work is that we only used one pre-trained model that was fully evaluated. Additionally, the image degradation was simulated through noise and blur rather than an actual clinical artifact image. And as we talked about, certain DCM cases produce minimal ED to ES changes. So that could lead to, since we had lower or lead to zero strain values, it could alter the average mean that we had for degradation. So in the future, we want to evaluate multiple pre-trained models, test the segmentation analysis on clinical MRI artifact images, most likely assess a larger patient data set since getting 1-0 could affect the mean a lot with a small data set. Additionally, investigate the HGM correlation between dice score and strain error.
And just to briefly conclude, we successfully completed all of our aims, and overall, our results suggested that MRI image quality can influence segmentation-derived cardiac measurements in disease-specific ways. So here are our references. And thank you so much for listening. We have a link to the collab below of our code. And yeah, any questions?
Thank you.
Thank you.
Oh, I think you're on mute.
Thanks. That was a nicely done study. What was your most surprising result, do you think?
I think especially seeing that the HCM dice score was high, but the strain error was Or I think it was the opposite. Yeah, the dice score was high, but the error was also high. I think that was confusing, at least for me, because I've never done like dice score before, so I was kind of confused why a good overlay could lead to a high error. That was just a little weird for us to see.
For me, also the fact that this, when you're doing this derived strain error, it looks almost independent of noise. The result, if you quickly look at it, you just say, well, wait, those first three, like I don't get any change at all. Obviously,
Yeah.
something.
And then once you hit high, it kind
Yeah.
of jumps up.
I know it's
Yeah.
surprisingly independent, and
Also, I
so
think we saw something similar for the dice score specifically for noise. Once it hit
yeah,
high, it dropped very quickly.
it catastrophically goes away,
Yeah.
but it doesn't seem to change the strain that much. So that's okay.
I think something in the future maybe too is to do more noise levels. So maybe you can see more of a trend as you grade
Right.
it. But I
Yeah.
think we've only hit 4 points. But
You're
in the
right.
future, yeah, that would be something to explore.
Okay, great. Thanks. Thanks, guys. Terrific. We're gonna move to team two. Evan, are you ready to take the screen? If you guys can unshare, or
Yeah.
that'd be great. And Evan, if you can share your screen, and here we go.
Yeah, right. Is that all visible?
All right.
All right. Hi, everyone. I am Evan, and today I'm presenting on my project about the effect of LG MRI image quality on the quantification of left atrial fibrosis for atrial fibrillation ablation planning. So, atrial fibrillation is the most common sustained cardiac arrhythmia, and one of the structural contributors is fibrosis in the left atrium. Fibrosis is important clinically because it can influence the success of catheter ablation procedures. And a common imaging technique used to assess fibrosis is LG MRI or late gadolinium enhancement MRI. In this technique, a contrast agent accumulates differently in healthy versus fibrotic tissue, causing fibrotic regions to appear brighter. However, there are challenges with this in that the left atrial is very thin, often only a few millimeters, and MRI is limited in spatial resolution. And in addition, images are affected by noise and motion from both the heart and breathing. And the main question becomes, how sensitive is fibrosis quantification to these image quality limitations? So for this project, I used the Utah MICAI 2018 left atrial dataset. I don't know if that's exactly how you say that, but that's what I'll run with. This is commonly used in cardiac MRI segmentation research, where each patient in the dataset has a couple different files, but the ones that I used were a 3D LG MRI volume and a corresponding binary segmentation of the left atrial wall. After loading the full 3D volume, I perform a slice selection step. Specifically, I compute the number of non-zero voxels in each axial slice of the atrial wall mask and select the slice with the maximum wall area. And this ensures that the analysis is performed on the slice with the most anatomically relevant information. And once selected, the MRI volume is converted into normalized intensity image for consistent processing across patients. And if you look to the top right over here, this is the image of the selected slice from my code, and the bottom right image is the left atrial wall mask over the selected slice. And since the dataset does not include a true ground truth fibrosis label, I estimated fibrosis using an intensity-based approach within the atrial wall. First, the atrial wall mask is used to restrict the analysis region, which reduces the background influence and focuses only on the anatomically relevant voxels. And then within this region, I computed the mean and standard deviation of voxel intensities, where fibrosis is defined as the pixels whose intensity is greater than the mean plus 1.5 standard deviations. And this approach was based on standard deviation thresholding techniques that were used in some LG MRI literature that I referenced for scar detection, where hyper-enhanced regions are assumed to correspond to fibrotic tissue. And if you look at the image on the right here, it's the selected slice where the regions of red are where my code estimates there to be fibrosis. Um, and to evaluate the robustness of fibrosis quantification, I simulate three distinct types of MRI degradation directly in MATLAB, each corresponding to a different physical imaging limitation. One, I use additive Gaussian noise. This simulates the reduced signal to noise ratio, which can occur due to acquisition settings or scanner limitations. And I implemented it using the imNoise function in MATLAB. Noise variance is systematically varied across multiple levels to simulate progressively degraded imaging conditions, and you can see that in the top right image over here. I think it's kind of hard to see the differences between that one and the original image. But I also applied motion blur, and this simulates cardiac and respiratory motion during image acquisition, which is a major source of artifact in cardiac MRI. And to do this, I generated a linear motion point spread function using the F special function and applied it using the imfilter function. And this models directional blurring caused by periodic motion during scan acquisition. And you can see that in this bottom left image over here, where it's pretty easy to see the blur compared to the original. And for the third one I did, I used resolution degradation, and this simulates reduced spatial resolution and partial volume effects. And I implemented this using a downsampling and upsampling approach using the im_resize function, which preserves image dimensions while reducing the effective spatial detail. And you can see that in the bottom right here. Also, kind of hard to see the differences between that and the original. Um, and to evaluate the impact of image degradation, like the previous group, I used the dye similarity coefficient, which measures the overlap between the fibrosis segmentation in the degraded image and the baseline segmentation. And the formula that I use is on the slide, where A is the baseline fibrosis mask and B is the degraded image fibrosis mask. And the Dice coefficient ranges from 0 to 1, where 1 represents a perfect agreement with the baseline. Um, and going into the results show a clear and consistent degradation in fibrosis segmentation performance as image quality decreases. But importantly, the magnitude and behavior of that degradation differs across noise, motion, and resolution. For Gaussian noise, the dissimilarity decreases gradually as noise variance increases. Just looking at the numbers, it goes from 0.69 down to 0.55 across the tested range, and you can see that in the top right graph over here. And this indicates that the segmentation is relatively robust to low to moderate noise levels. However, the decrease occurs because noise directly affects the voxel intensities near the threshold boundary, causing random fluctuations where pixels intermittently cross the fibrosis classification threshold. And this leads to small but widespread misclassification around the atrial wall. Going down to the bottom here for reduced resolution, the effect is more moderate and just stabilizes around the dice value of approximately 0.67 across the different resolutions. And if you look at the graph here, you read in the reverse where the higher the resolution size, the closer it is to the original. So that graph's kind of confusing, but um, it stabilizes around that 0.67, so it doesn't change that much either way. And unlike noise, the resolution loss does not introduce randomness, but instead reduces spatial detail. And this causes blurring of the atrial wall boundary and increases partial volume effects, where a single voxel contains a mixture of fibrotic and non-fibrotic tissue. And as a result, the segmentation becomes smoother, but not that drastically different in total area, which explains why the dice drop is less severe compared to that of motion blur, where motion blur had the most significant degradation, where you can see that graph over here in the middle, where the dissimilarity dropped sharply from approximately 0.66 down to 0.35 at higher blur levels. And this is a much steeper decline compared to both noise and resolution effects. And the reason is that motion blur is a spatially coherent distortion, meaning it systematically shifts and smears intensity patterns rather than adding random perturbations. And this directly affects the boundary definition of the atrial wall, localization of high intensity fibrosis regions, in contrast between fibrotic and non-fibrotic tissue. And as a result, fibrosis regions become spatially misaligned in the baseline segmentation, with the baseline segmentation leading to a much larger reduction in overlap. So in conclusion, the simulation shows that LG MRI image quality has a significant effect on fibrosis quantification. Among the tested factors, motion blur had the strongest impact, followed by noise and then resolution loss. And while it is already known that LGE MRI is sensitive to image quality, this project provides a controlled quantitative demonstration of how different types of degradation affect segmentation stability within a consistent framework. And clinically, this implies that variability in MRI acquisition quality, especially motion control, could meaningfully influence fibrosis estimates used in atrial fibrillation ablation planning. And future work could include extending this to multiple patients because I only ran my simulation on one patient, improving fibrosis segmentation beyond simple thresholding, and using a full 3D volumetric analysis. That was my presentation. These are my references.
Okay, thanks. So the quick question is, obviously the ImResize version of changing the spatial resolution didn't have much effect on dice at all, right? Because they were all like up to 4 digits or something. So do you know why that is?
Not sure. I think it did decrease the dice to like a baseline level, but then it just stayed around that level regardless of how much it changed. I tried to look into why that didn't change too much, but I couldn't find an answer for myself. So
Okay.
I honestly do not know
Okay, cool. Well, we'll figure it out someday. We'll figure that out, I guess.
why. Someday.
Yeah. Okay, cool. Thanks very much. Let's keep rolling. Team three. Um, can you take the screen? All right.
Can you see the screen?
Yep.
Okay.
Perfect. You can get
Okay.
off you go.
Okay, let's start. Good morning, everyone. We are the Team 3, and today we will introduce our project on beam hardening artifacts in contrast-enhanced cardiac CT perfusion imaging. The cardiac CT perfusion relies on high iodine enhancement to visualize the myocardial blood flow and the left ventricular blood flow. At higher iodine levels, the lower energy photons are preferentially absorbed, which produces the beam hardening. Since the myocardium lies directly next to the left ventricular cavity, this can create apparent myocardial hyperenhancement and mimic a perfusion defect. In this example, we can see that the conventional CT image and blood flow map both show an apparent low flow region, while the corrected image becomes much more homogeneous after reducing the beam hardening artifacts. This suggests that beam hardening is not only a physics issue, but also a potential interpretation problem in cardiac CT perfusion imaging. This raises an important question. If the higher iodine improves the enhancement, could excessive iodine also increase the defect-like artifact risk? Existing studies mainly focus on beam hardening correction methods, while the relationship between the iodine level and the defect-like artifact risk remains unclear. As shown in this conceptual plot, enhancement increases with iodine concentration, but beam hardening artifact also rises sharply at higher iodine levels, creating a possible defect-like region. Therefore, our research question is, at what left ventricular iodine level might beam hardening enter a defect-like range? We hypothesize that excessive iodine may increase the defect-like myocardial hyperenhancement.
Now let's look at some of the physics that drives this problem. In an ideal CT scanner with a monochromatic X-ray beam, the measurement follows the simple Beer-Lambert law. Projection equals linear attenuation coefficient times path length. One energy, linear relationship, perfect reconstruction, and stable Hausflug units. However, the real CT scanners at 120 kVp emit a polychromatic spectrum, a broad distribution of photon energies. The detected intensity is an integral over all energies weighted by the source spectrum and detector response. When we take the log to get the projection value, we run into the key mathematical issue. The log of an integral is not equal to the integral of the log. This is beam hardening. Low energy photons are preferentially absorbed as the beam passes through dense material. The spectrum hardens, the measured projection becomes smaller than the true line integral and Hausflug units in the shadow regions, especially the myocardium are biased downward. So why is iodine uniquely problematic even though standard beam hardening correction already exists? Standard BHC uses a polynomial correction calibrated for water, which has a smooth, gently decreasing attenuation curve across the clinical energy range. Iodine is different. It has a sharp KH at 33.2 keV in the 30 to 40 range. Its attenuation can be 40 to 100 times stronger than water, depending on concentration.
This creates a dramatic nonlinear absorption that the water-based correction cannot fully handle. When the LV contains high concentration iodine during first pass perfusion imaging, the actual beam hardening is much stronger than what the correction expects. The residue artifacts falls directly onto the adjacent myocardium, producing a dark shadow that mimics hyperenhancement from ischemia. This is why we rarely see this issue in routine coronary CTA. Its contrast is more diluted. To quantify this effect, we define a beam hardening index, BH of C, as the shift in effective photon energy caused by iodine. As the concentration increases, more low energy photons are absorbed, the transmitted spectrum hardens, and the effective energy shifts upward. We use this energy shift as a direct proxy for the strength of the beam hardening artifact. Our simulation model used three main inputs: the 120 kVp spectrum, NIST XCOM attenuation coefficients, and a simplified Kitagawa phantom. We tested different levels of LV iodine concentration, wall thickness, and projection angles.
Besides the theory part, we also built a model to simulate the iodine level and the variables. Our main goal is to turn the beam hardening mechanism into a simple threshold crossing model. And here we tested three variables, that is LV iodine concentration, myocardial wall thickness, and also the projection arc. Our main output is actually not a direct clinical HU value. Instead, it is a HU equivalent artifact index. We use this to compare relative artifact risk under different conditions. And here we use 20 HU threshold as a simplified defect-like threshold. And the question we mainly interested in is that under what circumstances does the artifact become large enough to look like a perfusion defect? So these slides show how the simulation works. We first build a simple phantom where the center part is simulated as the LV blood and outer ring is a myocardium. And then we adjust the iodine level, wall thickness, and angle as the input and calculate the beam hardening effect. And we will turn it into a HU-like artifact and adjust for the wall and angle. And finally check if it passes 20 HU. So for the first result, we fixed the wall thickness and the projection coverage. The only variable here is the LV iodine concentration. And as you can see from the figure, as the iodine concentration increases, the artifact index also increases. At about 12 microgram per microliter, it is around 21 HU, which crosses the 20 HU threshold. And at 24, it reached around 34 HU. So under this baseline condition, we can see that high LV iodine level can push the artifact into a defect-like range. And besides from the iodine level, we also check to sensitivity analyze, that is the wall thickness effect for the result 2 part. We assume that the shadow has a fixed width. So in a thinner myocardial wall, the same shadow occupies a larger fraction of the wall. So from the figure, as we can see, there are different wall thickness in different colors of line. At 24, the artifact index is about 68 HU for a 4 millimeter wall, and it's about 34 HU for an 8 millimeter wall. So the interpretation of this result can be that a thinner myocardium wall reduces the margin before the artifact crosses the defect-like threshold. And besides from the wall thickness, as our professor has mentioned, the projection angle will also take some effect during the simulation and also the real CT. So we test the projection angle coverage for the third result. So in the cardiac CT, the short scan acquisition is often used to reduce the motion. we approximated 180 degrees plus a fan angle as 240 degrees, for example, in this example, and compared that with a full scan with 360 degree. In our simplified model, the reduced angle coverage increases the relative weighting of the shadowed rays. As you can see from this figure, the artifact index is about 34 HU for the 360-degree scan and about 51 HU for the 240-degree short scan. So short scan can actually help reduce the motion, but it may also make the beam hardening artifact more likely to cross the defect-like threshold. This is only a very first-order approximation, but not a full fan beam CT reconstitution. And in the future, we may need more reality data to make more simulation. And then we connect our artifact index to the clinical interpretation. So as we can see, the real CT image have noise and measurement variabilities. So we add the Gaussian noise to simulate the artifact index. In this model, the noise has a standard deviation of 5 HU. So if the noisy measured value is about 20 HU, we count it as a potential defect-like artifact. The result shows that when the artifact is far below 20 HU, the crossing rate is low, but once the artifact gets closer to the threshold, the crossing rate rises quickly. So the takeaway of this clinical interpretation is beam hardening becomes clinically concerning when it approaches or crosses the defect-like threshold. So to conclude, our main simulation frame beam hardening as a threshold crossing problem. The LV iodine level is the main driver, and higher iodine level increases the beam hardening index and can push the artifact into a defect-like range. Besides from the main driven reason, thin myocardium and short scan acquisition are sensitive factors. They may reduce the margin before threshold crossing. But our simulation also have some important limitations. For example, it is the simplified 2D phantom, but not a real patient anatomy. And also the spectrum and annotation curves are approximate. And our output is actually equivalent index of instead of a clinical HU value. So these limitations needs future studies to enhance. But the value of our model is to compare the relative trends and show how contrast level autonomy and acquisition strategies may interact. And that is all of our project.
Great, thanks very much. And we'll have to defer questions because we're a little bit over time. There were 2 minutes over time. So, but thanks. Great simulation. Looks like important results. Very good. Team 4, can you take the screen
Yep.
and you can get going anytime.
Okay, can everyone see the presentation right now?
Yes.
Okay. Um, Good afternoon, everyone. My name is, sorry, good morning. It's still morning. Good morning, everyone. My name is Sardor Danier, and this is my partner, Matthew Callahan. Our project is titled Evaluating CT Partial Volume Effect on Lipid-Rich Coronary Plaque Characterization using Raman Spectroscopy. So the question we wanted to investigate was whether CT's partial volume effect can systematically misclassify lipid-rich coronary plaque, and whether Raman spectroscopy could provide useful molecular information for understanding those classification errors. So atherosclerosis is the buildup of fats, cholesterol, and other substances within the arterial wall, forming plaque. And so as this plaque accumulates, arteries can narrow and the blood flow can become restricted and increasing the risk of heart attack and stroke. So clinically, CT is widely used because it provides excellent anatomical information such as stenosis, plaque burden, and calcification. However, CT primarily measures attenuation and whether and therefore provides limited information about the underlying molecular composition of plaque. So Raman spectroscopy, we believe it can provide complementary information. So by measuring molecular vibrations, Raman produces a chemical fingerprint, which can be seen in the bottom right there, that can distinguish lipid-rich, fibrous, and calcified tissue based on composition rather than attenuation alone. So the difference between structural and molecular information was the reason that we decided to do this project. So the main CT limitation that we can focus on is the partial volume effect. So when a voxel contains more than one tissue type, as seen in this photo here, CT records a weighted average attenuation value rather than the true value of either tissue. And so at the tissue boundary, a single voxel contains signal from both structures. And because CT averages everything within that voxel, the reconstructed image contains a blurred intermediate region rather than a sharp boundary. And so this same phenomenon occurs in coronary plaque. And so lipid cores are often smaller than the dimensions of a clinical CT voxel containing lipid and fibrous tissues to be averaged together. And so to investigate this problem, we developed three specific aims. So the first aim compares how plaque composition is represented by CT attenuation versus Raman molecular spectra. And the second aim develops a synthetic plaque phantom and uses CT simulation to model how voxel size influences classification accuracy through partial volume averaging. And then the third aim over here explores a potential future direction for this work. The idea is to investigate whether Raman-derived molecular composition could help interpret ambiguous CT attenuation measurements and better quantify the failure modes in CT. So at this point, I'm going to hand it over to Matthew to discuss one.
Hi. So for our first aim, we want to make a forward model that could conceptualize how Raman scattering and X-ray attenuation are or are not coupled, and afford a sort of digital phantom with some simplifying assumptions. So essentially comparing the compositional mapping strategies between the two modalities. So the first thing that we did was we established a composition vector F that could hold some information that was asserting what's actually chemically present at each position in our digital phantom. So that holds like a volume fraction for lipid, fiber, and like calcified contributions. So this was like determined from like literature values. So if we follow that right, we follow the arrow right to CT, you can see how we start to process the CT data. So we just kind of go with a linear mixture model to produce a single scalar Hounsfield unit or value for that pixel, which encodes the degree of attenuation from the X-ray system. So very simple, but kind of gets the job done. We're storing all the values for what we think a lipid-rich, what a fibrous-like, or a calcified plaque should look like in theory in Hounsfield units in this vector H as well. And then we also have some noise term there, which I think may not have made it into the final code. And then if we take the Raman approach, that's where things kind of get a bit in the weeds. So we can create a theoretically distinct and deconvolvable molecular fingerprints, even in the mixed plaques, just based on the chemical composition of the plaque itself. And this is based on the types of chemical species present. This is just a property of the way that Raman scattering works. So that bold RV variable there is a 4-column matrix whose columns are the synthetic pure component Raman thesis spectra, which are determined from literature. So essentially doing the same function as the H that we showed before, but for each chemical we're looking for, we found some key points or I should say, local maxima on the Raman spectra that are commonly associated with those chemical species. So with those, we have the option of then fitting like a Gaussian at each of those positions and making a fake spectrum, which is we ended up doing. Or we could also go ahead and take that information and then do it the other way and extract back out those spectra if we wanted to using least squares or other linear regression methods. So we have a little bit of a method of going back and forth here, which is a unique strength of this, which could be useful, right? So the final products of this is that we have a single scalar attenuation value mapped to XY based on the F and H values for the CT, and we have a high dimensional molecular spectra mapped to XY based on F and RV. So if you hit the next thing, Sardor, okay. There we go. So that's kind of what I meant with like adding the Raman shifts together to get like kind of like a normalized spectra. So that gives a lot more information what we're doing. So if you move up towards the purple is kind of like the added together spectra that we're interpreting. Then if you hit it again, this is just like a very basic like proof that I could do it forwards and backwards, just on like some very basic data, but the lack of noise term kind of makes it a little bit benign. So continue forward.
Okay. So for AIM2, we directly modeled the partial volume effect using a synthetic plaque phantom. So the phantom consists of four tissue classes. So we have like lipid, fibrous tissue, calcification, lumen. And because the composition is known exactly, we can serve that as a ground truth reference here. And so the images at the top show the phantom's Hounsfield unit map, the tissue labels, and the Hounsfield unit distributions. And so we then simulated the CT imaging by varying voxel size from 0.2 millimeters to 1 millimeter. And so obviously, like as we increase the voxel size, it progressively blurs the tissue boundaries. And so at higher resolution, the lipid core is more distinguishable. And as voxel size increases, the neighboring tissues begin mixing within individual voxels, which is the message we're trying to get here. And so the graphs in the upper right quantify the effect that this causes attenuation values to shift away from their original tissue values and increase classification errors. So we observe that lipid core detection becomes less reliable as voxel size becomes larger, and the partial volume averaging increases. So it's important to note that the exact misclassification percentages depend on the phantom's geometry, the attenuation values, blur, blah, blah, blah. So the more important result is the overall trend here, where corsal voxel sizes increase averaging and reduce the ability of CT to accurately characterize lipid-rich plaque. So now I'm going to hand it back to Matthew for our final aim and future directions.
So moving through this pretty quickly, we weren't able to build the full spatial model with like the mapping onto the CT or anything like that, but I was able to extract these interesting little graphs that kind of showcase more on the Raman side of things versus the CT sides of things, whether or not the lipid fractions and the CT attenuation could be potentially related, so the actual lipid fractions, as well as the calcified fractions. This is kind of normal information. There's nothing too exciting here. Because you'd expect that as your lipid fraction increases, maybe your CT attenuation might decrease, right? And depending on the way that you scaled it. Now, for each point listed here, each one is theoretically a valid composition of F. So I constructed it such that each point would be adding to 1 with a full lipid, fiber, and calcium contribution. And then just kind of threw them at the math and saw what happened. But if you hit the next arrow here, we have some ones that are generated from the AIM1 data as well, but these are generated in a slightly different way in that I selected each of the points that were generated from there with like a little bit of noise introduced. So it kind of wiggled the points on the in the lipid fractions and renormalized them, so to speak. So that was kind of a pointless operation, I must admit, but it does definitely showcase that there's a very heterogeneous distribution, how some of these data could be read, and definitely a lot of room for overlap. So, I mean, if you just go across the CT attenuation range, you'll see that that's like definitely some crucial areas that were being interrogated before, and they're just absolutely full of points. So that alone is kind of, you can see how it could be confusing for the computer. Moving forward, back return to the nice version and then forward again. So the key takeaways here is that the CT attenuation definitely provides structural information, but may not accurately reflect the true composition of the plaque. The partial volume averaging can cause lipid-rich plaques to appear more fibrous. That was something that was demonstrated in AIM2. And the Raman spectroscopy does appear to provide finer, more useful molecular composition information and kind of allows like a one-to-one mapping between the two spaces, whereas the CT might be more many-to-one in that multiple CT values could represent one particular composition. As far as limitations, definitely synthetic plaque does have some limitations as far as how it can represent this full synthetic or the full chemical complexity because it can't really generate Raman spectra in their entirety. In addition, it's not really a routine measurement that would be taken for this. There's only a few data studies that we could check, and I was not able to download the big data that I wanted to my device, unfortunately. But yeah, it does not also capture the spatial representation or even the granularity of the sample. So if there's like very small pieces of calcium distributed throughout the entire sample, that might be not coming through properly. As far as future impacts, we'd love to extend this to like the spatial representation, make sure that we can really pair with the CT info and maybe really capture points on the edges of those features, because I think there might be a little bit of opportunity to inform the classification on that interface. And that's all. Thank you.
I
I
think
think
your
you're,
microphone is off.
Yeah, thanks, gentlemen. That was a hard topic to take on for a short project intern, but I like the construction, of the ramen tissue vectors and stuff like that. It was pretty clever. Okay, let's due to time, we're gonna have to keep rolling because we're running 5 minutes back. So team five, can you take the screen?
Oh, hi. Could you see my screen?
Yes.
Okay.
Uh, okay. Hi everyone. We're Group 5 and we're presenting our project about Carla, the cardiac agentic reconstruction and learning architecture. Our goal is making a multi-agent pipeline that converts 40 flow MRI case space into hemodynamic metrics with a deterministic physics verifier checking every state. We measure its false positive on phantom data, and this show it catching real failure on patient data and logging every decision on audit trail. And on the right is our user interface of our project, and we have input on the left, the live terminal in the middle, and the active agent indicator on the right. And next slide, please. And we outline 3 problems in our proposal. Here's what we delivered mapped directly to those 3 problems. For question 1, the coordination, we built an explicit multi-agent architecture, a planner, a plan critique, a coordinator, and 4 domain specialists for reconstruction, segmentation, verification, and hemodynamics. Crucially, every LLM call and every tool call is written to a machine-readable JSON audit trail. So when an agent make a decision, we know who decided and why and on what data. Question 2, a black box AI. Our physics verifier is implemented in pure Python. It's deterministic. It runs 4 physics checks: divergence, net flux, peak, velocity, phase unwrap. The LLM can interpret its predicate, but it cannot override them. That's our trust anchor. For question 3, pipeline complexity, we state the work into detect, recover, and learn. Each version builds on the last, and each produces evidence we can actually show.
So this is a system architecture. As mentioned in our proposal, we have 2 layers of agent, the general agents and the specialist layers. The physics verifier is an important component because it's the only piece in the whole system that's not an LLM. Instead, it's implemented in Python code. And while the LLM agents can interpret and explain its result, they cannot override its verdict. That's how we get a trust anchor at the bottom of every decision the system makes. We also added the Stanford aortic stiffness 40 flow dataset, a smaller LLM, QN 2.57b, and also built a brand new Streamlit UI. The Streamlit interface allows user to drive the whole pipeline through a browser rather than the command line. Now looking at the bottom table, this shows how each of the 3 datasets is used. The synthetic phantom is built by us with divergence equal to 0 by construction. We use it as a known good data for measuring false positive rates. The Stanford AS4DF, the one shown in the middle with the aortic shape, is a real physical 3D printed aorta image with MRI. And what's really nice about this data set is that it includes 2D PC MRI flow measurements at 7 anatomical cross-sections. This provides hemodynamics ground truth, which allows us to directly compare the actual flow number generated by our pipeline against those validated 2D measurements. And finally, OSU MR Synodo is a real patient case-based scan. We're not claiming clinical quality numbers on this data set because the image quality has no issue. Instead, we use it specifically to demonstrate that the verifier correctly flags failure where the data cannot be trusted. Next slide. How do we evaluate our pipeline? We inject 7 error types into a synthetic phantom. 3 are physics target errors, which are divergence, violation, a neck flux imbalance, and a peak velocity hotspot. The other 4 of them are corruption styles error that mimic acquisition or reconstruction failure, phase wrap, spatial aliasing, motion artifacts, and under convergence. Each type is applied at 8 magnitudes with 10 trials per cell, giving us 560 known bad cases. First, a compute budget. Each specialist agent has a hard cap on the number of reasoning rounds. So we tell the LLM at every step how many rounds remain. So it learns to wrap up and emit a report before running out. This can prevent runaway loops. And second, file access. Each agent has a permission list of which session directories it can read and how dataset paths are anchored in environment variables. So the LLM cannot make up a path or read another agent's outputs. Next slide.
Here's the results. On the left is the verifier's performance on the Phantom across all the good and bad trials. The 4 of 5 checks are reliable. They have the specificity equal or above 0.89, and the false positive rate is at most 11%. The one outlier is the divergence. It alerts on the clear cases far too often and drags overall false positive rates up to 38.9. On the right is our live run results. We will include a video demonstration of our pipeline submission. Each checks report pass, and in the detail that's reported in the JSON file. The hemodynamics analyzer shows the expect ranges and shows number on the right. The green mask overlay confirms the exact where the data had been checked run. We also have the output reconstruction image in the middle. The user can control the Z-scale and tuning the contrast for the best slice. And here's the Stanford 4D flow phantom. They have the 4D flow volume and the 2D phase contrast reference. So for the aortic anatomies, it's branched, so or net flux check assume a single inlet and single outlet, which will always return a false all the time. So we use the scope guard. Instead of just giving a false number, we ask it to skip when we detect the multiple branches. It prevents agents from feeding a fake number and run the metrics. On the left chart is the 4D flow from our pipeline and comparison with the 2D data that's provided in their repo. The mean flow paths have the correlated above 0.99, and the only thing is the BCT and the LSAs are weak vessels that might due to the 2D resolution limitation. And for results 3 is the real OSU data. The reconstruction agent runs the 50 iteration MATLAB recon code from them, so that it's MATLAB code. It's not generated reconstruction code every time. And it gives when the verifier returns fail because the physics check failed, the hemodynamic analyzer was never called since the mask was merging the aorta and the heart chamber together. So the number doesn't match, and it will give opposite directions, which like shows a positive flux and a negative, which we give up in the flow measurement. Instead of the LLM shouldn't just redraw the ROI and threshold, it should retry some different comparisons about contrast or try some new segmentation models. That's in our future work.
All right, so to wrap everything up, we built an auditable multi-agent 4D flow pipeline, which combines deterministic function skills and LLM agents that were quantified across 3 data tiers. And every decision is logged with a pure Python verifier that sits outside the LLM's control. And that verifier is what lets the agents fail honestly instead of confidently. So for future work, as you can see, we have 3 concrete next steps listed here. So first, apply the threshold recalibration we already computed because it eliminates the low frame rate false positives. Second, validate the flux checks are real data since they currently skip every branched case. And third, compare segmentation models such as the ones listed below since segmentation, not reconstruction, was where the OSU scan failed. And there are also 2 bigger questions that arise from this project. And for time's sake, I won't read them out. But these questions move us from a fixed pipeline to one that adapts. And the verifier makes that autonomy safe because it's the one that will check so the agents won't override.
Thank you. That's our references.
Terrific. Thank you very much for this, let's say, I guess it was a big lift to try and get this thing running in like 4 weeks or whatever, right? It seems to me this is like combining a large, AI pipeline / program with the game of telephone between these various agents. So it's interesting to, well, I guess we can discuss this offline, but the advantages of having them separate versus just trying to combine them into one massive, thing. But we can get into that. Thank you very much. Okay. Next, team 6.
Can you see this, the slides?
I think yes. Now we can.
Okay. Good morning, everyone. We are Team 6. I'm Xinyuan Long, and my partner is Yan Tonglong. So our project asks one question: can cardiac MRI tell us how old your heart really is? We call this the cardiac age gap. Predicts cardiac age minus your actual age. A positive gap means your heart looks older than expected. The gap is our main readout, not the age prediction itself. The diagram on the right shows the 4 logic. CMR goes in, and the deep learning model estimates the age, and we compare that estimate the chronological age to get a clinically useful residual. 2 people can be the same age and have completely different hearts. One has a normal ventricular function and flexible arteries. The other has a elevated mass, reduced ejection fraction, and a stiffened aorta. So the chronological age alone cannot tell them apart. This is where cardiac MRI comes in. CMR quantifies the phenotypes that actually change with aging: ventricular volume, ejection fraction, and myocardial mass, and the aortic distensibility. So our 3 aims follow from this. First, review which CMR phenotype are most aging sensitive. Second, define how to build an age prediction model from those phenotypes. And third, ask whether the age gap relates to the real clinical risk. And this slide lays out 2 papers our project is built on. So on the left, by Nature Medicine 2020, they analyzed a lot of UK biobank participants and identified 82 cardiac and aortic phenotypes that shift systematically with age and sex. Things like LV mass going up, ejection fraction going down, and aortic distensibility dropping as the arteries stiffen. This established that CMR image carry real aging informations. And on the right, ACRE 2024, they applied a ResNet-based regression model to roughly 40,000 UK biobank subjects across 7 organs, including a lot of heart MRI cases. The model predicts not just an age estimate, but also an uncertainty value. So you know how confident each prediction is. So together, BI shows what to measure, and ACRE shows it can be modeled. Before getting into the pipeline, we want to be upfront about scope. We synthesized the funding from 2 UK biobank studies, one defining age-sensitive phenotype, one demonstrate deep learning organ age estimation, and translated them into a concrete cardiac age gap line pipelines that is ready to execute given data set. The left side of the slide shows what the look like in practice. Published CMR phenotype results, published biological age result, and the evaluation framework. The right last side lists what a full implementation would actually require: approved access to the raw CMR images, chronological age and sex labels, image quality control, and clinical metadata like hypertension, diabetes, lipids, and the disease outcome. So the reason we are showing the distinction is that the clinical validation step testing whether the age gap predicts the real outcomes depends entirely on having that metadata. Without it, you have an interesting model, but not a useful biomarker.
Right. All right. So this slide shows the method for a full cardiac age gap model. On the left is the reference architecture from ACRE's 2024 paper. It is a ResNet-style regression model, and the key idea goes beyond the architecture name. The model predicts 2 outputs: the mean predicted age called mu, and the uncertainty called sigma. That uncertainty matters because medical images can vary in quality, scanner setting, and patient anatomy. So the model should express how confident it is for age prediction. The middle pipeline shows how this becomes our cardiac MRI framework. And the input is linear CMR, such as short axis or long axis images. The model can use either segmentation derivative phenotypes, like a ventricular volume, mass, and ejection fraction, or image-based CNN features directly. Then it predicts cardiac age, and we calculate the cardiac age gap as predicted cardiac age minus chronological age. The right box shows how we would evaluate. MAA tells us the average error in years. Pearson correlation tells us whether predicted age tracks real age. Age gap plots and then calibration check whether the model is consistent across age, sex, scanner, and image quality. And finally, risk association tests whether the gap leads to hypertension, diabetes, lipids, CVD, or HCM. Next slide, please. So our results section is based on reviewed published evidence, focusing on what has already been demonstrated for imaging-derived biological age. The large plot on the left comes from ACRE's 2024 paper. It shows predicted age gap across chronological age groups. In this modified Bland-Altman style plots, the zero line means predicted organ age matches chronological age. Points above 0 mean the organ appears older than expected. Points below 0 means it appears younger. And this plot is useful because it shows more than a single average error. It helps us to see whether the model tends to overestimate or underestimate age in certain age ranges. The chart on the right summarizes organ-level prediction performance. For heart MRI, the ACRE paper reports 39,432 heart MRI cases, a heart MAE of about 3.42 years, and a correlation of about 0.87. And the interpolation is focused on important. Heart MRI provides an approximate aging readout and contains measurable age-related signal. And this is support the feasibility of a cardiac age gap readout and motivates the next step of the clinical validation. Next slide, please. Okay. So now let's move from prediction performance to clinical interpretation. The figure on left is from BASE 2020 paper. It supports the idea that CMRI phenotypes are associated with non-imaging clinical variables. That matters because our goal goes beyond predicting age. Our goal is to ask whether cardiac age gap captures risk-relevant remodeling. The middle visual shows organ age gap relationships. The key point is that the age gap can represent structural biological signal. Some age gaps show biological plausible relationships, especially between paired or related organs. That supports the idea that the residue may contain biological information. The right side addresses the extreme HCM example for a 30-year-old patient with hypertrophic cardiomyopathy. A large positive cardiac age gap is possible because HCM can cause abnormal cardiac remodeling. The careful interpretation is that the gap may reflect disease-specific remodeling or a case that differs from the training population. So clinically, a high cardiac age gap should be treated as a flag for review and risk modeling rather than as a standalone diagnosis. And next slide. All right, so our conclusion is that the cardiac MRI-based age prediction is feasible, and its translational value depends on the cardiac age gap. So first, CMR carries aging-sensitive structure and function signals, including ventricular volume, ejection fraction, myocardial mass, strength, and aortic features. And second, our project synthesizes the published evidence and proposes a cardiac age gap framework. And this makes our conclusion a feasibility-based and framework-level interpretation. And third, the next step would be acquire approved patient-level CMR images and clinical metadata, train and calibrate the model, and test whether cardiac age gap predicts risk factors, disease labels, or outcomes. So overall, cardiac MRI can support an interpretable cardiac age gap biomarker when combined with the calibration, uncertainty reporting, subgroup testing, and clinical validation. And thank you. Yeah, next slide should be our reference. Yeah.
Okay. All right, thanks. So it seems to me there is a correlation there to disease, although the point you were making is that in some cases it's an actual clinical disease that is causing the heart to look older, and so that might not be a good thing to include in the model. Is that correct?
Yeah.
Yes.
Okay, so we've got that. And then when we're finished, the difference in age, like the change from the correlation one was like 3 years. Is that what it was like from start to finish?
Yeah, the MAE would be 3.42 years.
Okay. So just from common sense and the people you know, are you going to worry about 3 years difference
For
when you're
some,
75?
yeah, we also noted that question. So for special patient, maybe 3 year is a big problem. However, if we consider the mean of the patient, I think
Yeah.
3 year is not a
Yeah. So I don't know. I think there's a signal there, but I'm not sure the signal as a predictor for an individual. You'd have to work pretty hard to prove to me that I'm going to worry about that much, you know?
Yeah.
Anyway, so that's a great look at that data, and great that you saw all of that UK Biobank data and everything. That's terrific. Okay, thanks. Let's keep rolling here, and we got teams 7 up next gen pet. Terrific. We can see your slide.
Okay, so hi everyone. Today we're going to be talking about our project, which is next gen PET tracers and myocardial viability. So normal myocardium has adequate blood flow, normal contraction, and healthy metabolism. Hibernating myocardium, by contrast, is still alive but receives chronically reduced blood flow. The tissue reduces its function to conserve energy but remains viable and can potentially recover if perfusion is restored. Infarcted myocardium has been permanently damaged and replaced by scar. Since the cells are no longer alive, function cannot be recovered through revascularization. This distinction drives treatment decisions. Viable tissue may benefit from surgical procedures to restore function and improve outcomes. Truly infarcted tissue is managed with medical therapy and symptom control. The challenge is that hibernating myocardium can appear non-viable on imaging, and if it's incorrectly classified as scar, patients may miss the opportunity for potentially beneficial revascularization. So currently, one of the gold standards for assessing myocardial perfusion and viability is rubidium-82 PET imaging. Rubidium-82 behaves like potassium, so it's naturally taken up by living myocardial cells. After injection, it emits positrons that produce gamma rays detected by the PET scanner, generating a 3D image of the heart. Areas of reduced uptake indicate reduced blood flow or tissue damage. The problem lies in the physics of rubidium-82 itself. It emits relatively high energy positrons that can travel between 2 to 17 millimeters before annihilation, but the myocardial wall is only 8 to 12 millimeters thick. So this causes signal spillover beyond the true tissue location, blurring the image and reducing spatial resolution. Small regions of hibernating myocardium can appear infarcted as a result. Since treatment decisions depend on correctly identifying viable tissue, this resolution limitation has real clinical consequences, and improving it is the motivation for our project.
So, building off the limitations of RB82 imaging, our project investigates whether F18 labeled tracers can help improve myocardial viability assessment through enhanced PET physics and tracer kinetics so that we can better detect these small regions of hibernating myocardium. So F18 emits lower energy positrons with a shorter positron range, reducing the spatial blurring and also improving edge definition between the viable and scarred tissue. This allows us to better see the smaller viable myocardial regions to be detected within the surrounding infarcted tissue. The F18 tracers also have higher extraction fractions, meaning that more of the tracer moves from the bloodstream into viable cardiomyocytes, producing a stronger and more reliable PET signal. And biochemically, these tracers target the mitochondrial complex 1 within the electron transport chain. So because these viable cardiomyocytes maintain active oxidative metabolism and mitochondrial function, the tracer is preferentially retained in living tissue while scar tissue shows reduced uptake and rapid signal washout. In order to simulate tracer behavior, we use a one-compartment kinetic model where the tracer enters the myocardial tissue through the uptake constant K1 and leaves through the washout, which is shown in K2. Different K1 and K2 values were assigned for healthy hibernating and scarred myocardium, and these viable myocardium maintains mitochondrial function and complex 1 binding, leading to higher tracer uptake and slower washout, which provides a sustained time activity curve. In contrast, scar tissue shows lower uptake and rapid tracer clearance, which would result in a lower and flatter curve. We then used MATLAB's ODE45 solver to generate these time activity curves for both F18 and RB82 for a comparison. And overall, the model evaluates whether the higher uptake, slower washout, and longer half-life of the F18 tracers help to provide better separation between viable and non-viable myocardium.
So in our simulation, the arterial input function, or AIF, is our system's input, which just simulates a approximately 10-second tracer bolus. We modeled this using a gamma variate function where the parameters A, alpha, and beta define the dose intensity, speed of injection, and rate of blood clearance. For this simulation, we standardized all three of these to A being 15, alpha 2, and beta 1.4. We kept these constant across all tissue types so that the differences in our final time activity curves are just a result of the tissue biology, specifically the K1 and K2 values discussed previously. So we calculated the blood-to-tissue influx rate, K1, using a modified Rankin-Krohn equation. This takes into account absolute myocardial blood flow and the specific capillary permeability surface area product of the tracer found through literature values. The tissue-to-blood clearance rate, or K2, determined by the ratio of K1 to the tracer's apparent cellular volume distribution, also helps us in our equations, which allow us to both simulate how different tracers behave in varying tissue conditions and compare to each other.
Here are the parameters that we've inputted into our simulation. Blood flow reductions across tissue types modeled as identical for both tracers allowed us to see the differences decreasing from healthy to hibernating to scar tissue, but they all did differ in their volume of distribution, which is reflected in our code. This table just shows us our calculated K1 and K2 values. Here, the slide shows up how we set up our simulation. So at the top is our main one-compartment ordinary differential equation. We modified it by adding lambda, which is the physical decay constant, to ensure that our model can account for the tracer actively decaying while it is still in the heart cells. For healthy tissue, we modeled a high K1 value and moderate K2. For hibernating tissue, we simulated a perfusion metabolic mismatch where influx is low, but clearance rate does drop because the tracer does get trapped inside cells viable mitochondria. For scar tissue, we modeled a match defect where both blood flow and influx are very low and the tracer can quickly wash out because the dead cell membranes no longer hold on to it. We calculated this physical decay constant lambda as natural log of 2 divided by the tracer's half-life, which comes from solving a first-order exponential decay differential equation. We normalized both values to minutes in our code. For F18, the half-life is 110 minutes, which gives us a very low lambda value of 0.0063, making signal loss from decay almost negligible. For rubidium-82, on the other hand, the half-life is only 75 seconds, which leads to a very large lambda value of 0.5545, meaning that over 55% of the signal intensity vanishes every single minute. So we included realistic models as well for noise using a Poisson noise model, where F18 has a low noise coefficient and rubidium's is higher due to its higher inherent positron range. So this slide here just defines the two primary clinical metrics that we use to evaluate our simulation results, which are the signal to noise ratio and contrast to noise ratio. The SNR just measures our overall image purity and statistical quality, whereas the contrast to noise ratio is the ultimate metric in clinical decision making because it can tell us how easily a doctor can distinguish between hibernating and scar tissue. So here are the results of our simulation. On the left is the F18 fluoroperidase profile. Even with a standard clinical dose, the curves for healthy hibernating and scar tissue are very smooth and clean, and they are widely separated over the entire 30-minute window. And that results in a high SNR value of 98 and a CNR of 43.4. The middle plot shows us the results for rubidium-82. We gave it about 10 times higher initial bolus to fight the physical decay, and that's pretty consistent with what clinical dosages are. And the rapid signal loss and high noise coefficient here do cause the curves to become very jagged and unstable. And the signal of the tracer does decay very fast, so the curves do kind of squash together, which gives us an SNR of 18.8 and a CNR of 5.8. The bar chart on the right kind of quantifies all this and shows how F18's combination of a longer half-life and highly targeted mitochondrial binding can outperform rubidium, providing the high contrast data that clinicians can use to confidently identify viable tissue.
The significance of this work is that accurately distinguishing viable hibernating myocardium from scar tissue is critical for treatment decisions in ischemic heart disease. Misidentification can prevent patients from receiving beneficial procedures or can also lead to unnecessary high-risk interventions. By improving spatial resolution, tracer retention, and contrast noise ratio, these F18 tracers can provide a more accurate myocardial viability assessment and help to improve patient selection. Future directions of our project include expanding the model beyond our one-compartment system to a multi-compartment system to better represent the tracer transport and mitochondrial binding. And additional studies could also incorporate cardiac motion and patient-specific variability to better simulate what real clinical imaging conditions would look like. We could validate this with clinical PET datasets, and AI-assisted image analysis, which can help further improve non-invasive cardiac viability assessment and personalized treatment planning. Thank you.
Terrific. It looks like the F18 has crushed the rubidium. Is there, when you look at the literature now, does anybody use rubidium anymore? Like, or has it been completely taken over by this F18 agent?
I think it's a pretty novel tracer, so not really, but I think it's also just easier accessibility wise for other not metabolic based tracers like rubidium and the other tracer on Karina's slide, I think.
So basically this one is so new that it's hard to get or it's like really expensive or something?
Yeah, I think it's just pretty new, so they're kind of still working on advancing availability of it. Yeah.
Okay, great. Well, I know what to get when I go to the to get my PET scan. All right, thanks very much. Great job. So now we're gonna do one more. We're gonna go a bit over time, but we're gonna do photon counting. This is team 8 versus energy integration.
Hello, can you see it?
Yes.
Okay. So hello everyone. We are team 8. So our project title is photo counting CT versus energy integrating detector CT. So one limitation of conventional CT in cardiovascular imaging is being hardening artifacts. In coronary CT angiography, image quality is very important because the scan is used to evaluate coronary artery disease and guide clinical decisions. However, the heart is a difficult imaging target. There are dense structures such as calcium in coronary plates, ribs, spine, and iodine contrast inside left ventricle and blood pool. When a polychromatic X-ray beam passes through these dense materials, low-energy photons are observed first. The remaining beams becomes harder, meaning its average energy becomes higher. So the problem for EIDCT is that it combines all photons energies into one total signal. It does not directly know how the spectrum changed after passing through calcium or iodine. This can cause cropping artifacts, streaks, and incorrect actual values. Clinically, this matters because the image may not reflect the true tissue signal. It may affect stenosis evaluation or myocardial signal interpretation. So the motivation of our project is, can photon counting CT reduce the problem by keeping energy information instead of mixing all energies together? So this slides shows the key difference between EID-CT and the PCCT. Traditional EID-CT measures the total deposited X-ray energy in each pixel. In simple terms, it adds all photon energy together and gives one broadband signal. This is useful, but it loses spectral information. After the beam passes through calcium or iodine, EID cannot tell how that energy spectrum has shifted. But PCCT works differently. It counts individual photons and sorts them into different energy beams. So in our simulation, we use two energy beams, 25 to 65 keV and 65 to 120 keV. This allows PCCT to keep partial spectral information for each pixel. And the main advantage is that in each energy beam is narrower, so it behaves more like a monochromatic measurement. This makes the reconstruction less sensitive to beam hardening. And the PCCT can also reject low-level electronic noise using energy threshold.
And for this slide, I will briefly explain how we built the simulation. The key idea is to keep the physics setup fixed and only change the detector model. And this lets us to isolate the effect of energy resolve detection. First, we generated a polychromatic X-ray spectrum using a test-like model. This represents a realistic CT beam with many photon energies. Second, we built a simple one-dimensional cardiac phantom. The ray passes through soft tissue, calcification, iodine-filled LV blood, and then the same structure on the other side. This simplified geometry captures the two key high attenuation materials in cardiac CT, calcium and iodine. For EID-CT, all photon energies are subbed into one broadband signal. As the beam passes through dense material, low energy photons are observed first, so the spectrum becomes harder, but EID cannot directly measure that spectral shift. For PTCT, photons are separated into two energy beams, 25 to 65 and 65 to 120. By processing these beams separately, PTCT approximates a more monochromatic reconstruction and reduces spectral mixing. Finally, we compared the two methods using SNR, Hu era versus monochromatic ground truths and cupping artifact. One limitation is that our PCCT correction is simplified, so this is a mechanism focused simulation rather than a full clinical reconstruction. Next, please.
Our results beam is the physical foundation. On the left is figure 1, showing the energy-dependent linear attenuation coefficient mu for our three tissue types, derived from the National Institute of Standards and Technologies photon cross-section database. The key observation here is the iodine blood curve in gold. It sits above the other two at low energies, and more importantly, it has a sharp discontinuity at 33.2 kilo electron volts. And that's the iodine K edge marked by the red dotted line. Below this threshold, iodine absorbs X-rays extremely strongly through the photoelectric effect. Above it, the absorption drops sharply. This spectral feature carries critical diagnostic information about the iodine concentration. The energy integrating detector computed the tomography cannot see it because it sums all the photon energies into a single number. The photon counting computed tomography's energy beams split at 65 kilo electron volts, shown by the dashed line, separately process the low energy and high energy portions of the spectrum, capturing this spectral structure. And now on the right, the figure 2 shows our central simulation result, the Hounsfield unit profile along the central rays through the phantom. The gray dotted line is our monochromatic ground truth. The blue is energy integrating detector computed tomography, and the gold is photon counting computed tomography. In the outer soft tissue regions, all three lines align well. The beam hardening hasn't built up yet, so both detectors perform similarly. But inside the iodine blood left ventricle, the chamber in the center, the energy integrating detector diverges from the ground truth and it enters the chamber high, then drops as the spectrum hardens across the 20 millimeters of iodinate blood, creating a slope that doesn't reflect true tissue properties. The photon counting computed tomography tracks the ground truth considerably more closely throughout. And this Hounsfield unit drift in the energy integrating detector directly translates to inaccurate contrast quantification in clinical imaging. Next slide, please. Moving to our quantitative metrics, the left chart shows the signal-to-noise ratio across all three tissue types, and the right shows absolute Hounsfield unit error relative to the ground truth. In the soft tissue, both detectors perform similarly. The signal-to-noise ratio of 2.1 for energy integrating detector versus 4.4 for the photon counting computed tomography, with Hounsfield unit errors around 46 and 35 respectively. And this is expected that beam hardening is minimal before the ray encounters any dense material. And the difference becomes dramatic at the calcification. The photon counting computed tomography signal-to-noise ratio reaches 82.1 against energy integrating detectors 28.9, which is a 184 improvement. On the error side, the energy integrating detector deviates 49 Hounsfield units from the ground truth, while the photon counting computed tomography reduces this to 31 Hounsfield units. And this happens because the calcification layers harden the beam as the ray passes through, shifting the effective spectrum and causing energy integrating detector to misestimate the local attenuation coefficient. The photon counting computing tomography's beam correction compensates for this shift. Next slide, please.
The main conclusion is that PCCT changes CT from one mixed energy measurement into a spectral reconstruction problem. This matters because beam hardening is caused by spectral mixing. In EIDCT, all energies are combined. So once the beam is hardened, the detector cannot recover how the spectrum changed. And PCCT helps because narrower energy beams behave more like monochromatic measurements, which can stabilize the signal near calcium and iodine. However, our model is still simplified. It is one-dimensional, does not include scatter or realistic noise, and does not perform full material decomposition. So the next step would be to extend this to a 2D reconstruction at poison noise and test iodine K edge or material decomposition method. Overall, PCCT is not just a detector upgrade, its energy beam architecture directly addresses the physical cause of beam hardening artifacts. Also, the final quantitative performance still depends on the reconstruction method. And next is our references.
Okay, great.